to Mechanical Pros. I'm here with Jeff, and today we're going to be talking about premature motor bearing failure with a variable frequency drive. Jeff, this is something that we see in the field all the time in our industry. VFDs causing premature bearing failures in motors. Tell me what causes a VFD to create a bearing to prematurely fail?
Variable frequency drives are a switch device. So what happens is we take an AC, we turn it into DC, and then we switch it at a very high rate of speed. What that does, it creates a parasitic voltage that travels through the output leads of the drive and enters the magnetic field of the electric motor. Finds a ground path, and the only ground path in electric motors is where the bearings make contact with the motor frame.
So when you say parasitic, are you saying like, so there's electricity that's leaving the main, like the sine wave, and it's trying to find somewhere else to go?
Right, it's trying to find a source. It's trying to find a path to ground. So what it is when I say parasitic, it travels in a magnetic field. So it's not like voltage that you would see being transmitted through wire. It's almost like a static electricity. Okay. It seeks that ground source, and what it does is as it enters the magnetic field, goes out through the bearings, and it creates a pattern in the outer races of our bearings. It starts out as a frosting, what they call either frosting or railroad tracking.
You have an example of a bearing that we have.
Right. And if you'll take a look at this, outer races the balls are supposed to run in a machine surface. And so what happens is as that voltage begins to transverse inner race through the ball to the outer race, it creates that frosting pattern, and over time will become what we call pitting. Almost looks like a railroad track.
Okay, I got you.
And so if you take a look a little bit closer, you can see this pattern beginning to develop.
Oh yeah, right down there through the center.
Okay.
Where the bearings are running.
Right, so what happens is it causes that ball to run over a rough surface, the ball gets hot, begins to expand, and the bearing fails prematurely.
The premature failure is basically, in layman's terms, electric current finds a ground, and the ground is the ball bearing to the bearing ring.
Correct.
Right. And I know ceramic bearings were a one-time solution. Mm-hmm. Tell me about ceramic bearings.
They operate by isolating the ground path. But what happens is the voltage is still being created. So what it does is it'll transmit, go ahead and go into the rotor of the motor, and it will stay there. And a lot of times the rotor will get hot simply because we keep inducing voltage into that rotor. So without a ground path, it's going to continue to fail that rotor, or it will transition and go to your driven load. And if there's any bearings on those bearings will be affected.
Okay. Yeah. So ceramic bearings is still a solution.
It's still viable.
What's the difference between a grounding ring and ceramic bearings?
Well, a grounding ring, what it does is it gives least path of resistance for that voltage to find ground. A grounding ring is much like what you see here, and what it does is it's exactly that. It attaches to the motor frame, and these are carbon fiber brushes that are on the inside. Now, if this ring was sized for this motor, it'd be much smaller, but it's 360-degree contact on the shaft. The ring is grounded. Yeah. And so it's less resistance than the bearings are to get to ground. So the rings were highly effective, but it's the same thing like what we used to have. We used to start out with carbon brushes that were spring loaded. Mm-hmm. They wear out quickly, and then they're a maintenance item. And a lot of times they don't get maintained properly, problem comes back. Same thing as what we're finding over time on the Aegis ring, or on the...
So grounding ring, basically you're just taking these carbon fibers, they're touching the shaft, taking it to a ground.
Taking it to a ground path. We're giving it a better ground path.
All right, cool. But these fibers eventually can wear out, and
and they're subject to installation process.
Okay. Tell me about CoolBLUE. CoolBLUE is a new solution, or a newer solution to us that we've had great success with. So tell me about that.
What we've done is we've applied it in the field, and we've actually collected some empirical data, and we find it to be very, very effective. Parasitic voltage seeks a magnetic field. And so what we're doing is we're basically creating a magnetic field primary of the motor magnetic field and capturing it and holding it in suspension.
Okay, so tell me what CoolBLUE is.
CoolBLUE is basically, it's what they call nanite crystal, and it's a ferrite. And what it does is it's just like what you would have like a current transformer. Okay. And so what we do is when we capture that, we hold it there, and then when we collapse the field, it dissipates naturally. Okay. What we have is we have it installed on this drive. Now this drive here has a bypass on it, but what I need to explain is that the variable frequency portion of it, these mount on the output between They mount between the output of the drive and the input of the motor. And basically what we'll do is, as you see here, there's two parts to this, okay? The blue cores, the CoolBLUE cores, do the majority of the work and capture the majority of that parasitic voltage. On the bottom, what you'll see here on top of the overload are individual Nala cores. Okay, the Nala cores are there to capture any residual voltage that may escape the CoolBLUE cores. Okay, an installation on this, obviously, we have three-phase output going to a three-phase motor. So on this particular application, all you really have to do is the output of the drive is actually connected to an output mechanical overload. So really all you have to do is you lift those three leads, you slide the CoolBLUE cores on, which is this device here. And then what you do is you go ahead on each individual wire, mount the Nala cores. Okay. And then you just reattach that. We put this system here in about 15 minutes.
Okay. So you're taking your output leads off, and you're running your this is the CoolBLUE, and then the smaller ones that are Nala cores.
Yes.
Right.
Right.
And then so the main CoolBLUE, the big shield, I'll call it that, is all leads are going.
All three go
all
through
three
those.
leads are going through this.
Right.
And then these Nala cores are picking up each individual.
Right.
leg.
Because as we
Right.
pass all three phases through the CoolBLUE cores, that's what makes the magnetic field. Just like the three-phase input to the motor, we're making a three-phase magnetic field in the CoolBLUEs. And then individually on each lead, the Nala core is capturing any residual.
Awesome. So what's the maintenance on a CoolBLUE product?
There's really not any. The maintenance itself, it's just like you would maintain the inside of this drive. You just want to kind of keep them clean. You want to make sure that they don't touch any live parts. And then as far as service life, they'll last for the life of the drive.
Okay. All right. Awesome. And pretty easy, fast to install?
Very easy, very fast to install. Really, it's all about planning and getting in there and taking a look at where you can get them in there. Because you'll see, it takes a little bit of room, and this is a pretty tight panel, and we were able to get them in there. The difference between like a system like this is going to run, a few $100. When you start addressing by putting Aegis rings on there, they're substantial. Their cost is much higher than what you would pay for that. But then you also have the maintenance and the installation cost. And you got to be fairly skilled.
Yeah.
Because you got to make sure you put them in there the right way. You got to make sure you get them on a shaft, and you got to make sure the surface is clean, because that was one of the other drawbacks is if where the brush rides, if you get any type, if your housekeeping isn't all that great, anything that gets in there and insulates that shaft, you lose the ability to give it a ground path. So it had some drawbacks. So cost-wise, I'd say that this is fractional compared to other methods that we've used in the past.
A cost-effective, permanent solution to prevent premature bearing failures.
Absolutely.
When you're running motors with a VFD. So tell me, one last question. So at what size drive, what size motor, when would I apply a CoolBLUE solution to protect my motor bearings?
Well, it's they're rated by horsepower and they're rated by length of lead. And there's a point of diminishing return at some point in time. When you start talking in the fractional horsepower is all the way up to 5 horsepower, we can replace those motors for about $300 to $500.
Okay.
And so we're going to be as effective. But what we're finding out on service life on some bearings with parasitic voltages, they're only lasting 90 to 120 days. So,
based on the application, maybe anything over 5 horsepower.
Anything over
sense.
5 horsepower,
Okay.
I would absolutely suggest that we install.
Awesome. Love talking drives, love talking motors with you. Man, you're one of the best. So thanks for checking us out here on Mechanical Pros. Hit that like, hit that subscribe, come back, check us out, and hopefully we'll bring y'all some more really good content.